Okay. Hello and welcome to my talk. As Kiara said, we will be looking at chapter 2 of the Rust Atomics and Locks book written by Mara Bos. This is, in my opinion, one of the best books about concurrency and writing safe Rust code with multiple threads. So I'd highly recommend that you buy this book if you haven't already. My name is Anup and I work at Salesforce. I've been dabbling in Rust for just over a year now. I have done some parallel programming in the past, mostly in Java, but that was ages ago. So, and these are some of my socials. You can find me on Twitter, GitHub, LinkedIn. Okay, so here's a rough agenda. We'll talk about the following. Very high-level overview of atomics. We'll also revisit some of the concepts from chapter 1. We'll look at 3 types of operations that you can do with atomics: the load and store operations, fetch and modify operation, and compare and exchange. These are basically different ways of accessing and modifying values that are stored inside of the atomic types. As we'll see shortly, you don't access the values directly, but you'll always use one of these operations or methods to access the values. That's it. We'll summarize it at the end. So the word atomic comes from the Greek word atomos. It means something that is indivisible, something that cannot be cut into smaller pieces. In the context of computer science, it means an operation that is indivisible. It is either fully completed or it didn't happen yet. As we mentioned in chapter 1, when multiple threads try to read and modify the same variable or memory location, it could potentially result in undefined behavior. But atomic operations allow multiple threads to safely read and modify the same variable. And because such an operation is indivisible, it either happens completely before or completely after another operation. And that's how it avoids undefined behavior. Now, one of the topics that we should revisit from chapter 1 is the cell type and the concept of interior mutability. You can think of cell as a shareable, mutable container. It wraps a T, but allows mutations through a shared reference. It provides interior mutability, where you can modify the value stored in cell through an immutable shared reference of the cell. And it does that by moving values in and out of the cell. So if the value inside the cell is of type copy, then the get method returns a copy of T. If the value inside the cell is default, then the take method moves out the contained value, leaving a default in its place. And the set method puts the modified value back in C, or the cell. The key takeaway is that a cell can't directly let us borrow the value it holds. We need to move a value out, leaving something in its place, modify it, and then put it back in order to mutate its content. Both cell and ref cell exist to allow mutability of a shared reference in a controlled manner, but they only allow this in a single-threaded way. Neither cell nor ref cell are thread safe. They don't implement the sync trait. Okay, so cell can't be used within a single thread. The atomic types represent a concurrent version of a cell. Just like a cell, they avoid undefined behavior by making us copy values in and out as a whole without letting us borrow the contents directly. This is a massive simplification. And if you crack open an atomic type and look at the source code, I believe the actual implementation uses unsafe cell rather than the cell type. But this is a good enough approximation, or at least a good enough mental model for atomics. Now, unlike a cell, they cannot be of any arbitrary size because there is no generic atomic over type T. There are only specific atomic types like atomic U size, atomic U32, atomic I32, or atomic bool, and we'll look at those in a bit. Also, atomics allow different threads to safely read and modify the same variable. Now, because such an operation is indivisible, it's like I said before, it happens completely before or completely after another operation, and that's how it avoids undefined behavior, which kind of implies that if you don't have multiple threads, then it's unlikely that you'll need atomics. Is there a question? I think I saw something.
I think you're all good for now.
Okay, for now? Okay. There was a Discord notification. I think I'll switch that off. Okay. You can see my screen, hear me? Yep.
Yep.
Okay, good. Awesome. Now, Rust has copied the memory model for atomics from C++20. And that's not because this model is the best or even easy to understand, as you'll see in chapter 3. It's rather a pragmatic concession to the fact that modeling atomics is complicated. So at the very least, we can benefit from existing tooling and research around the C++ memory model. Atomic operations are they're the main building block for anything involving multiple threads. All of the other concurrency primitives like mutexes and condition variables, they're all implemented using atomic operations. Mutexes are a bit higher up in the abstraction, and atomics are low down in the abstraction. So, and I think mutexes are built using atomic types and atomic operations, I believe. These operations are available as methods on the standard atomic types that live in the std sync atomic namespace. And they all have names starting with the word atomic, such as atomic I32 or atomic U size. And unlike most types, they allow modification through a shared reference. And this is, of course, possible due to interior mutability. Okay. Let's start by understanding how the code you write is modified by the compiler and the processor. You may or may not be aware that both compilers and CPUs reorder the code we write if they think it will lead to fast execution. And they perform all sorts of tricks to make your program run as fast as possible. A processor might determine that two particular consecutive instructions in your program will not affect each other and execute them out of order if that makes your code faster. Now, let's say that one instruction is blocked because it's fetching some data from main memory, then the processor might decide that maybe some or several of the following instructions might be executed or finished before the first instruction finishes, as long as that doesn't change the behavior of your program, and that's key. And similarly, a compiler might also decide to reorder or even rewrite parts of your program if it has reason to believe it might result in faster execution. It's all about speed. But again, only if it doesn't change the behavior of your program. Now let's look at this example. Here the compiler might determine that the order of these operations does not matter because nothing happens between these three add operations that depend on the value of pointed to A or pointed to B. So it might reorder the second and third operations and merge the first two into a single addition. Then while executing this function that's optimized by the compiler, the processor might decide to execute the second addition before the first one because the value, just as an example, because the value of B was available in an L1 cache, but the value of pointed to A had to be fetched from the main memory. So it decided to kind of switch it around. Now, in this case, the end result stays the same. The value in the pointed to A is incremented by 2, and the value in B is incremented by 1. The logic for, how do I say this? The logic for verifying that a specific reordering or optimization won't affect the behavior of our program does not take other threads into account. If our program here, in our program here, that's fine because the compiler guarantees that because we have the exclusive reference to A and B, nothing else can possibly access the value, making other threads irrelevant rather. The only situation where this is a problem is when we are mutating data that's shared between threads, which is the case when we are working with atomics. And this is why we have to explicitly tell the compiler and the processor what they can and can't do with our atomic operations, because their usual logic ignores interactions between threads, and they might end up performing optimizations that will probably change the result of your program. And that's not good. So when you call methods on atomic variables like load and store here, you have to pass in an enum called ordering, which determines what guarantees we get about the relative ordering of operations. In essence, the ordering enum specifies the way atomic operations synchronize memory, or it tells the compiler the set of guarantees you expect for this memory access with respect to things that might be happening in other threads at the same time. Don't worry if that didn't make sense. We'll cover ordering in detail in chapter 3, but I think it's a way to tell the compiler and processor don't reorder certain things at a very high level in very simplistic manner. I think for this chapter, if you understand that, that's enough to understand the atomic operations. And the simplest variant in this enum with the fewest guarantees is relaxed. They can be freely reordered and provide no happens before relationship. Again, all of these terms, we'll explore these terms in detail in the next chapter. What does happens before mean, what's a memory model, and all of that stuff. Relaxed still guarantees consistency on a single atomic variable, but it doesn't promise anything about the relative order of operations between different variables. In this chapter and in the talk today, we'll use a relaxed variant in all of our examples. And in chapter 3, we'll look at the concept of memory ordering in more detail. And again, if you're familiar with multi-threading programming in C++, then they should look familiar because Rust's memory orderings are the same as those of C++. Right, so the first two atomic operations we'll look at are the most basic ones, load and store operations. If we take atomic I32 as an example, you can see the function signatures for load and store method here. The load method atomically loads the value stored in the atomic variable, and the store method atomically stores a new value in it. Now, note how the store method takes a shared reference rather than an exclusive or mutable reference, even though it modifies the value. Again, the reason is interior mutability. We talked about that earlier. But another reason is because the compiler generates special instructions that make it safe for multiple threads to access the value at the same time. Let's look at some examples to understand these two operations. Now, the first example uses an atomic bool for a stop flag. This flag is used to inform other threads to stop running. Yeah. So here we are importing atomic bool and the relaxed enum into our module. Atomic bool is a Boolean type, which can be safely shared between threads. This type has the same in-memory representation as a bool. And here we are creating a static variable called stop and initializing it with the value of false. Again, we don't have to use the mute keyword, even though we will be updating its value later using the store method. And the store method uses interior mutability to update the value in stop. Okay. Here we are spawning a background thread that is repeatedly running the sum work function in a while loop. We can assume that the sum work function is performing an expensive operation that takes some time to complete. And the while loop checks the stop atomic bool flag to decide if it should continue or quit the loop. The main thread allows the user to enter some commands to interact with the program. In this example, the only useful command is stop to make the program stop. If the user types stop on the command line, then we store the value true in stop variable, which will then be read by the background thread to stop the while loop. Now, this simple solution works great as long as the flag is regularly checked by the background thread. If it gets stuck in that sum work function for a long time, then that can result in an unacceptable delay between the stop command and the program quitting. Right? Let's look at another example. In this example, we'll process 100 items one by one on a background thread, while the main thread gives the user regular updates on the progress. Again, we are bringing atomic size, type, and scope and declaring a variable called num_done, which is of type atomic usize with an initial value of 0. Here, we are using scoped thread, which will automatically handle the joining of the thread for us and also allow us to borrow local variables. Now, every time the background thread finishes processing an item, it stores the number of processed items in the num_done variable, okay? Whereas the main thread shows that number to the user to inform them of the progress roughly about once per second. And once the main thread sees that all 100 items have been processed, it exits the scope, which then implicitly joins the background thread and informs the user that everything it's done. Once that last item is processed, it might take up to 1 whole second for the main thread to know, again, introducing an unnecessary delay at the end. And if we want to avoid that kind of delay, we can use thread parking to wake the main thread, which we looked at the concept of thread parking in chapter 1, so I'm going to skip the theory, but here's an example of how to do that. Nothing much has changed here. We now have a handle to the main thread through the thread current method, which is now used by the background thread to unpack the main thread after every status update. So it's similar to the previous one, but now it's using the unpack method on the main thread. And the main thread uses the park timeout method rather than sleep. So it can now be interrupted by the background thread if needed. Now, any status updates, they are immediately reported to the user while still repeating that last update every second to show that the program is still running. Okay, the last example before we move on to more advanced atomic operations is about lazy initialization. Now, imagine that there is a value X, which we are, let's say, reading from a file, or maybe getting it from the operating system, or calculating it in some other way that we expect to be constant during the run of the program. We don't expect X to change, and we can request or calculate it only the first time we need it, and then remember the results. It's sort of like we're caching X, or the value in X. The first thread that needs it will have to calculate the value, but it can store it in an atomic static to make it available for all threads, including itself if it needs it again later. Okay. Now we'll assume that X is never 0, so we can use 0 as a placeholder before it's been calculated. Then we load the value of X using the relaxed memory ordering. Then we check if X is still 0, and only if it is 0, then we calculate the value. Otherwise, return the loaded value of X from the function. In other words, any call to get X will see that the value in the static is non-zero and return it immediately without calculating it again. Yeah. Now let's say we have one thread calculating the value of X, then a second thread calls get X while the first one is still calculating X. And the second thread will also see it as 0, and it will also start calculating X in parallel. Now, one of the threads will end up overwriting the result of the other, depending on which one finishes first. And this is called a race. Now, just to be clear, this is not a data race, which is undefined behavior and impossible in Rust without using the unsafe keyword. But it's still a race with an unpredictable winner. Now, since the result will be the same regardless, in this case, it doesn't matter who wins the race, but you're wasting processing cycles here. If calculate X is expected to take a long time, it's better if threads wait while the first thread is still initializing X to avoid unnecessarily wasting processor time. Now, you could implement this yourself using condition, variable, or thread parking. But the Rust library supports this functionality through something called as once and once lock. So you don't need to implement these yourself. We don't cover this implementation in this chapter. I'm not sure if we cover this in later chapters, but yeah, we don't cover this specific implementation of once and once lock here. But just information that you can use these instead. Okay, let's move on to more interesting operations, the fetch and modify operations. These operations load or fetch the original value and modify the atomic variable as a single atomic operation. So if we start at the top, we have fetch add and fetch sub, which perform addition and subtraction. These are the most commonly used. But we also have other operations like fetch OR, fetch NAND, fetch XOR. Function definitions are self-explanatory, I hope. The one exception in terms of naming the function is the last one, which is called swap. It's an operation that stores a new value regardless of the old value. So instead of calling it fetch store, it is being called swap. I guess it makes sense because store in the context of atomics has a special meaning, and therefore swap is a better function name, just to be aware. Right, so quick example of how fetch add function works. We assign A to 100. We increment A from 100 to 123 using fetch add, and then it returns to us the old value of 100, which we then assign to B. Any load operation after that will see that value of 123. And we can assert that B is the old value of 100 and C is the new value of 123. And both the fetching and adding operation happens atomically. Right, let's look at some more examples. So in the first example, we'll reuse the progress reporting example from before, where we used an atomic usize to report the progress of a background thread. Now I'm showing that previous example on the screen here. Now imagine that if we had to split the work of reporting progress over multiple threads, we'd need to know the progress from all of those threads. And we could use a separate atomic usize for each of those threads and then load them all in the main thread and then sum them up. But an easier solution is to use a single atomic usize to track the total number of processed items over all of those threads. So let's update that example to split the work over 4 threads. So a few things have changed. Num_done is now a reference, and we'll see why. And we now spawn 4 background threads rather than 1, and use fetch add instead of store to modify the num_done atomic variable. We also use a move closure for the background threads. This closure captures the variable t, to know which of the 4 threads it is, and whether to start that item at 0 or whether to start it at 25 or 50 or 75. Now, without the move keyword, the closure would have tried to capture t by reference, and that isn't allowed, as the value of t exists only briefly during the loop. And as a move closure, it moves or copies its captures rather than borrowing them, giving them a copy of t. And because it also captures the num_done variable, we've changed that variable to be a reference, since we still want to borrow that same atomic usize. The atomic types do not implement the copy trait, so we'd have gotten an error if we had tried to move one into more than one thread. So that's why it's a reference. Okay. Now in the main thread, we load the num_done variable and check if it has reached 100, at which point it will break. Otherwise, it will print the progress of the work being done. We don't know in which order the threads will increment num_done, but as the addition is atomic, we don't have to worry about anything, and we can be sure that it'll be exactly 100 when all threads are done. Okay, so let's continue this concept of reporting what other threads are doing through atomics. Let's enhance our previous example to also collect and report some statistics on the time it takes to process an item. So on top of num_done, we are adding 2 more atomic variables here. We are adding total time and max time to keep track of the amount of time spent processing items. We'll use these to report the average and peak processing times. Okay. The background threads now use something called instant now and instant elapsed to measure the time they spend in process item function. An atomic add operation is used to add the number of microseconds to total time, and an atomic max operation is used to keep track of the highest measurement in max time. Okay. The main thread divides the total time by the number of processed items to then get the average processing time, which then reports together with the max time. Yeah, pretty simple. If we just enhanced it to capture more stats. Now, because the three atomic variables are updated separately, it's possible for the main thread to load the values after a thread has incremented num done, but before it has updated total time, which could result in an underestimate of the average. It's a subtle nuance, and this is important because we're using the relaxed memory ordering here. It doesn't give any guarantees about the relative order of operations as seen from another thread, okay? It might even briefly see a new updated value of total time while still seeing an old value of num done, which could result in an overestimate of the average. Just something to be aware, not a huge issue here for our program. The worst that can happen is that we'll briefly report an inaccurate average to the user. If you really want to avoid this, you can put the three statistics inside a mutex, or we'll look at other memory ordering in the next chapter on how to do this if you want to enforce a happens before relationship between these variables. Now, if you use a mutex, there is obviously an additional cost of locking and unlocking the mutex and then potentially temporarily blocking other threads. So there's a performance penalty. Okay. So let's move on to a use case where we actually need the return value from fetch add. Now, suppose we call some function called allocate new ID that returns a new number every time it's called. We might use these numbers to identify tasks or maybe other things in our program, things that need to be uniquely identified by something small that can be easily stored and passed around between threads, such as an integer. Now, implementing this function turns out to be trivial using fetch add. And in this example, we are simply keeping track of the next number to give out, increment it every time we load it. And the first caller will get a 0, the second will get a 1, the third will get a 2, and so on and so forth. Here's an example of calling this function from the main thread and then from 4 parallel spawn threads. The only problem here is the wrapping behavior on overflow. I believe all fetch operations overflow when they reach the max limit. So in this case, the 2 raised to 32nd call to allocate new ID will overflow that 32-bit integer, and the next call will return 0 again. Now, whether this is a problem really depends on how likely is it going to be called, or rather how often, and what's the worst that can happen if the numbers are not unique. Now, if memory safety is dependent on these numbers being unique, then this implementation is not acceptable. And one solution could be something like this. We can try to make the function panic if it is called too many times. For example, the assert statement here will panic after 1,000 calls. We're just making that number up. We're saying once it reaches 1,000 calls, panic. This version is problematic because the assert panic happens after the atomic add operation already happened, meaning that the next ID has already been incremented to 1001 when we panic. So if another thread then calls the function, it will increment it to 1002 before panicking and so on. One solution is to not panic, but instead completely abort the process on overflow. And the std process abort function will abort that entire process, ruling out any possibility of anything continuing to call our function. That's one way of doing this. Another way to deal with this is to use fetch sub to decrement the counter again before panicking like this. It's still possible for the counter to very briefly be incremented beyond 1000 when multiple threads are executing this function at the same time, but it is limited by the number of active threads. Now, if you still don't want this, there is a third way of tackling this, which is arguably the correct way, at least according to the book, because it prevents the addition from happening at all if it would overflow. And the third way is to use the compare and exchange operations, which is the final set of operations that we'll look at today. These are the most advanced and most flexible atomic operations. This operation checks if the atomic value is equal to a given value, and only if that's the case, replace it with a new value, all atomically as a single operation. It will return the previous value and then tell us whether it replaced it or not. Its function signature is a little bit more complicated than the ones we've seen so far. And if you ignore the memory ordering, it is basically identical to this implementation, except it all happens as a single indivisible atomic operation. So what's going on here? You load the value into a variable v. We check if v is equal to the expected value. And if it is, only then store the new value. Otherwise, leave the value untouched and return an error variant. Essentially, we can load a value from an atomic variable, perform any calculation we like, and then only store the newly calculated value if the atomic variable didn't change in the meantime. Okay, as a demonstration, let's increment an atomic U32 by 1 without using fetch add, just to see how compare exchange is used in practice. First, we load the current value of A. We calculate the new value that we want to store in A, not taking into account potential concurrent modifications of A by other threads. We use compare exchange to update the value of A, but only if its value is still the same value that we loaded before. And if A was indeed the same as before, it is now replaced by a new value and we are done. Now, if A was not the same as before, another thread must have changed it in the brief moment since we loaded it. The compare and exchange operation gives us the changed value that A had, and we'll try again using that value instead. Now, the brief moment between loading and updating is so short that's unlikely for this loop, to loop more than a few iterations. Yeah. Let's look at how we can tackle the overflow problem in our ID allocation program that we saw earlier. So we have the same example as before, but now we are using the compare exchange method. In fact, the eagle-eyed amongst you have probably noticed that we are using compare exchange weak instead of compare exchange method. The difference is that the weak version may still sometimes leave the value untouched and return an error variant, even though the atomic value matched the expected value. Apparently, using weak is more efficient, especially when you're using it in a loop. I don't know why. The book says we'll cover the why in chapter 7. So we'll find out in chapter 7 why this is more efficient when you're using it in a loop. And just like before, you're creating a static variable next ID of type atomic U32 with an initial value of 0. Then you're loading that value in the ID variable. Then you're running a loop, and inside it, you're calling the compare exchange weak. And you're passing the ID, which is the expected value, ID plus 1, which is the new value, and then the success and failure memory ordering. And we know that if it's successful, then we return an OK, or we get an error variant. We're checking and panicking before modifying next ID. We're basically guaranteeing that it will never be incremented beyond 1,000, and therefore making that overflow thing impossible that we had before. You can actually replace all of the above with this very handy method called fetch update. It's the same as the load operation, that we saw before, followed by a loop that repeats a calculation, and the compare exchange weak that we just showed you. Now, we're not going to look at fetch update in this book so that we can focus on the individual operations. Okay, so in the lazy initialization example we saw before, we made a function that lazily initializes a value on the first call, but reuses it on later calls. Now, when multiple threads run that function concurrently during the first call, more than one thread might execute that initialization. And they will override each other's values, which could result in unpredictable order. This is fine for values that we expect to be constant, but there are use cases such as the value gets initialized to a different value each time, even though we need every invocation of the function within a single run of the program to return the same value. For example, imagine a function called getKey that returns a randomly generated key that's only generated once per run of the program. Now, it could be an encryption key that's used for communication with the program, which needs to be unique every time the program is run, and it stays constant within that process. So here's an implementation of that idea. Now, we only generate a new key if key was not yet initialized. And then we replace key with our newly generated key, but only if it is still 0. If we swap the 0 for our new key, we return that newly generated key back. And new invocations or any invocations of getKey will now return the same new key that's now stored in the key variable. And if we lost the race to another thread that initialized key before we could, then we forget about our newly generated key and just use that value from the key instead. And this is a good example of a situation where compare exchange is more appropriate than its weak variant, because also we are not using this in a loop. Yep. Nice. So that brings us to the end of our chapter. To summarize, atomic operations are indivisible. They are either fully completed or they haven't happened yet. They're done through atomic types like atomic I32, atomic U32, etc. Not all atomic types are available on all platforms, although the book doesn't provide more details on this yet. And relative ordering of operations is tricky when multiple threads are involved. And we'll look at memory ordering in detail in the next chapter. Yeah, simple loads and stores are nice for very basic inter-thread communication. We saw examples like the stop flags and status reporting. Fetch and modify operations, they are great for a small set of basic atomic modifications like addition, subtraction, and or swap. That are especially useful when multiple threads are modifying the same atomic variable. Finally, compare and exchange operations are the most flexible in general, and they're the building block for making any other atomic operation. And we'll explore atomics in the next chapter. Especially we'll look at memory ordering in detail. Again, thanks for your time and your attention. I'd like to reiterate how amazing this book is, and you should support Mara's work by buying a copy for yourself. Thank you. I'll take questions now. I'll try my best to answer them.
Awesome. Thanks, Anup. That was great.
Cool. Thank you.
Does anyone have any questions?
Thank you very much. I really like how you started with combining the C++ knowledge you had with these multi-threading and with a memory model. I just made some notes. So it was really insightful. Single in the last ones. It's always like a lot of us are more or had more experience with C++, and I always search for bridges like pack and unpack. I think you don't have it in.
Sorry, Tim, you're breaking up a little bit there.
Okay. Let me check.
Are you compiling something?
No, I just switched the microphone now because I think this Bluetooth thingy microphone is not as good. I wondered about pack and unpack, if there's something similar in C++ standard. So just
pack and unpack.
Yeah, the thread parking and unparking.
Oh, don't know. I'm not sure. I don't know what that does. Yeah.
There was much at the beginning. Yeah.
I don't know if there's an equivalent of like the unpack primitives.
Yeah, because I just implemented something last week, and That would be great there. So
oh, sorry. So your question is parking and unpacking. Parking is there something synonymous in C++?
Yeah, that's.
I haven't a clue because I've not done C++ programming, multi-threaded programming ever. I've experienced in Java, but when I borrowed some of the concepts from chapter 3, where it's mentioned explicitly, and then I went and read the C++ memory model before this talk, and it's more or less the same. So one of the good references for understanding this in more depth is the Nomicon. I think that Nomicon does a good job of explaining some of the parallels between how Rust does memory ordering and the memory model and how that matches with C++. Yeah.
Hi. Ask a quick question as well, please.
Yeah.
So I'm fairly new to Rust and systems level programming, so I'm just doing this to brush up as well. So these atomic operations, if I understand, sorry, can you hear me clearly? Am I too far away?
Yeah.
These atomic operations, if I understand it correctly, usually the system scheduler will like hard switch between sort of threads, etc. when it's executing those threads instructions. So it'll have to like in context for the given thread. You're saying these atomic operations are a case of once they start executing, they're almost being guaranteed not to be switched to executing on another thread, so to speak. Is that
no?
Be indivisible, and once they must be either completed. It must be completed before any other operation.
So based on my understanding, at the atomic level, I think they will complete the update that they're doing. But the interesting thing is if the OS does switch threads, if you specify the ordering correctly, it will see the right update for that variable. So let's say, for example, if you're doing an update to an atomic U32 variable, let's say you're using fetch add and you're adding 100 to it. Depending on the memory ordering that you specify, if the OS switches thread and if the new thread then tries to load the value, and then what value it sees is dependent on the memory ordering that's been specified for that operation. So if it's relaxed, there is no, and we'll go into detail in this on how this will work in the next chapter, but there is a happens before relationship that's established between what value the other thread will see when it's trying to get that value or execute that same statement. And it's dependent on what's happened before in another thread.
Okay. I don't fully get it, but with most things, you have to sort of think about it and cycle through it multiple times. I'm already starting to see where this is sort of going.
Yeah. I think correct me if I'm wrong, Kiera. I think, but in chapter 3, we'll go into more detail about the whole happens before relationship and what does it mean to give a more, there's an acquire and release ordering, consistently sequential ordering, and all that stuff. So,
and in terms of how it's done at a hardware level, so I think that's kind of the crucial bit about atomic operations that makes them different from other operations that you're doing in Rust, is that they are implemented at the hardware level. So for what you were talking about there in terms of context switching of the threads, I'm not sure off the top of my head in terms of whether it could put something to sleep midway through, but nothing else could operate during your operation. So no other threads will ever see a half-written piece of memory. That's the crucial bit. So if I need to write a U size, I'm not going to get halfway through that write operation and then have something else come in and read some half-written memory. That's never going to happen. It's either not been written to or it has been written to. And that's implemented at the hardware level, which is why you can have that kind of support. And that's why it differs by operating system. And depending on, if you're running x86 or you're running something else, then you'll have different behavior. And that's something which we're going to get onto in later chapters. So I don't want to say anything wrong. So I'm going to refrain giving more detail.
So interested already, right now. Okay. Thank you very much for that. I appreciate it.
Yeah, so that raises a thrill because I'm also read about the sins of the hardware stuff that it's depending on I think on the instructions of x86 and also the ARM processors. What I think is really interesting is if you don't work with atomics, what may happen, maybe, I'm not sure, is that you can write with one thread and at the same time read and have some of the bits written and others not written yet. So you would have a data race then. And well, with the atomics, you get this new problem about if you write code in a specific ordering, like you have in your source code on line 1, you have this atomic variable, and Anup, you describes it quite well. The compiler then, and even the processor can decide about the ordering. I think then we get more control about turning off these optimizations to be more sure.
Yeah.
And you hit on a really crucial bit there. It's more than just the compiler, the processor itself. You might be reading the memory at different points. So the layers involved in your CPU. So you've got your 4 threads, but then you have several layers of caching. And then it's only at the very bottom of all of those layers of caching is the true memory that you're trying to read or write to and from. So depending on how far down it's gone, how much synchronization has happened, you could be reading something totally different to what you thought, and it'll all be, very small time frames, very, these types of bugs, it'll be happening 1 in a million, and it will be a massive pain. But that's why these hardware primitives exist.
Yeah, and one of the things to keep in mind when you're writing multi-threaded programs is the program that you write will be changed by the processor and the compiler. If they think that if it'll make the code performant, they will introduce new things or move things around. So don't make any assumptions. In fact, one of the things that we'll talk about in chapter 3 is called an out of thin air values, which the compiler will introduce these imaginary or random values in your program to speed them up. And sometimes they could introduce very difficult to debug bugs. Yeah. So always assume that your code will not run in the same order. Once the CPU and the compiler is done with the program, they could reorder your program or insert new instructions, and that could have an impact. And that's why atomics are very useful, because then you can specify regions in your code to tell the compiler, don't touch this region or do this region in this specific order. And that's why memory ordering is very useful.
And another thing as well, I'm still trying to get my head around the whole send and sync sort of market traits as well. Are these atomics, are they send and sync as well? I suppose they are, because they're sort of be used by meetups.
So the way I think about these are at level of abstractions. So send and sync are marker traits that you can use to specify your types, whether they are send, which means that type can be sent to another thread, or whether they are sync, which means that type, the data in that type can be shared with another thread, and that's available in your the foundation Rust, and all of the other stuff, atomics, mutexes, channels. They are all in the standard library. So these are all high-level abstractions. So the way I think about it is, you have send and sync marker traits that you almost all primitive types are both send and sync. You can also create your custom types, which are send and sync. Then above that, those are atomic types that you can use for atomic operations and defining these atomic types that are safe to use for shared state concurrency. And then above that, you have mutexes, which are high level abstraction, which are built using atomic types. And mutexes have the performance penalty of you have to lock something, acquire a lock and release a lock, which means you have wasted processor cycles. You have to cater for that. And then you have the channels wherein you don't share any data, where you just pass messages between threads. And I think we should always consider using channels first, if that satisfies your use case, and then look at mutexes. And if mutex doesn't satisfy your use case, then look at atomics, because using atomics on its own can, at least the code that I've tried to that I've seen so far, can be quite unwieldy is the term I'm looking for. But yeah, you have to really put a lot of thought, and it's very the notorious thing about atomic code is it's very difficult to test, because of the different hardware architecture. It might work on your machine for 10 years, but then it might not work on another machine which has a slightly different architecture. So it's very difficult to test this code.
Yeah. Okay.
And just to mention about sharing atomics. So atomics are sync, which means you can pass around references, which is what Anup demonstrated. But what you'll quite often see, if you're not using a scope thread, you'll still need to put it into an arc. You'll still need to put it into an atomic reference counter type. And that's just because it's still a reference at the end of the day. And I mean, you could send the atomic, but then you're just sending an atomic. You could send a U32, but it's not shared then, is it? So you would need to share it by either sharing a reference, but then your lifetime rules come into play, or by sticking it into an atomically reference counter type so that you can have multiple references to the same atomic.
Yeah.
Because I could have sworn I've seen you use, I just saw you use just atomic just by itself when spawning multiple threads. Or was that just because you were using the share?
That was a static atomic. So sorry, that's a special case as well.
Just keep the example simple.
Static.
Yeah.
So static means it lives for the entire duration of the program. So you're essentially referencing the same data. You're right in the sense that you're not actually moving the value into the thread. You're essentially referencing it from the thread, but you don't run into lifetime problems because you've got something that's static, so it lives for the duration of the program.
We were cheating there, or rather Mara Bos was cheating, because she was trying to focus on the operations, because if you didn't use static, you'd have to kind of use all of these other things like arc and other stuff that might have taken the focus away from the operations that we are trying to understand.
And I think
so we cheated.
Even if you're using static, you would run into a problem with the move keyword, which is why she then changed it to a reference in the next example. Because if you're moving it, you would still be moving it into the example, and then you wouldn't be referencing the same data anymore. I think I need to reread the chapter, but yeah.
All gets very tricky. There's a time you're just using just an atomic U size with a standard let, but then because you use a scope thread, and then you did the num_done.store, which was essentially just using the reference to it. I think that's why it all worked.
Yeah.
Things like that. So it all became quite. So I was getting a bit confused for a little bit, but I think it all makes sense now.
I can see a hand up there. Jade, did you have a question?
Hi, yes. Can you all hear me?
Yeah, we can hear you.
Okay. I just wanted to ask, and it may be a bit out of scope, but since Kara mentioned that there's certain processor instructions that, like, based on which architecture you're using, may be different. So atomics, are they implemented? So is there like an x86 or x86-64 instruction that's specifically atomic that would be called in that case, or is it just the order in which the assembly instructions or the CPU instructions will be called?
So I think your platform has to support atomic type. I'm not exactly sure what that means at a deeper level. The second thing is the ordering bit. So for example, if I were to take x86 and x86 64 architecture, even if I provide the relaxed ordering, I think it's a no-op on those architecture, because it'll still try to do a release and acquire, or it'll apply more stronger ordering on it. Whereas if I use an ARM architecture, it will, if you provide relaxed ordering there, it will actually behave in a way that the ordering was relaxed, which means between threads, the ordering is not guaranteed in that sense. But in a single thread, it is guaranteed.
And I've dropped a link in the chat, but I'll just share screen to show it as well. Will I? sorry, I might not be sharing screen because for some reason the window's not coming up. But I've just sent a link to the summary of what we're going to get onto, which is the end of chapter 7. And that contains a really brilliant summary of the assembly instructions that are available on, a couple of the key instructions that are available on different hardware. So you can see there's some differences between ARM and x86 and 2 different versions of ARM. But it's those atomic operations that are the key ones that make it atomic. And then the reason why within, or my understanding anyway, of the reason why within Rust and within C++ and other languages, they have concrete atomic types, is they restrict you to just atomic operations. That's the difference. So I mean, you could do an atomic add with, well, this is my understanding, you could do an atomic add with a regular like U32, but you can still do other stuff. Therefore, it's not an entirely atomic type. So in order to make it atomic, you need to only be using atomic operations on it. And to indicate that those are the instructions you want to generate, you need to use the atomic types built into the language that know about the operations that are available on the hardware you're using.
I think we should do chapter 7 sooner rather than later. I think that's an interesting chapter. It's almost like an independent chapter, right? Oh,
it is, like, for me, it's the reason I want to read the book is chapter. I'm super hyped.
Hey, thank you.
Cool. Any more questions?
I think that's everything. Thanks so much, Anup. And so the next meetup is in 2 weeks. It's on the 31st of May. That'll be going over ordering chapter. Super excited for that. And then the following one, Tim has kindly volunteered to take on chapters 4 and 5. That's going to be building a spin lock and channels. So those are some types you might have heard about. Channels definitely heavily used, so excited to see those implemented. But we still have an opening for chapter 6. So if anyone would be interested in presenting a chapter, it's a really, really great way to read it, knowing that you're going to get asked questions on it after. It really cements it a bit more. So I'd highly recommend it. Just drop a message in the Discord, or you can message me directly. And yeah, also there's later chapters in the book as well. So yeah, see you all then.
Thanks all.
Thank you very much. See you.
Thanks.
Thank you.
Bye.